Take you through the second part of the fundamentals of chemistry. So this goes alongside the first video, which is part 1. And in this session, we're going to look at the structure of the atom and being able to label the structure of the atom. That is an expectation in both higher and foundation tier. We're then going to talk about electron configuration, being able to draw atoms, for example. And then we're going to talk about isotopes and what isotopes are. And in particular, we're going to look at the isotope calculation that you are expected to be able to do. So we looked previously in the part 1 section of this video at how the structure of the atom was developed to that which, in terms of which we have today. So you were looked at the Rutherford experiment and how that actually helped to come up with the model that we have for the atom today. And we're going to draw the model here because it is an expectation, particularly on foundation tier and combined science, that you are able to label the atom and being able to tell us a little bit about it in terms of its charge and its mass. So that's what we're going to look at now. So we're going to draw a basic structure of an atom. And as you know, if I teach you, I can't draw for love nor money. So here is a basic structure of an atom. And if you're asked to label it, you need to know 4 things. And I'm going to do a little squiggle here for that 4th one there. So you need to know the names of each part. So we'll start in the center, okay? That there is what we call the nucleus of the atom. And the nucleus of the atom is made up of 2 subatomic particles. And the first particle is positively charged, and that is a proton. And that's how I remember it. Positive P, positively charged are our protons. In the nucleus also, you have got neutrons. And they are both in the nucleus of the atom. And we're going to talk about what that means in terms of mass and charge in the table below. But it's important you're able to identify them on the diagram. And then around the nucleus in shells are our electrons. Okay, and they sit on the shells and they follow the rules, as we'll talk about later in the video, in terms of how we put electrons onto shells. So this is the basic structure of the atom. You are expected to be able to draw that, label it, identify the parts. So it's important that you do get that clear in your heads. But we're going to talk now a little bit about these 3 things. So the 3 subatomic particles are our electrons, our neutrons, and our protons. And you do need to know a little bit about them. So we'll start off with our protons. So we know from the diagram that protons are positively charged. So they are positive, okay? And because they're in the nucleus of the atom is the part of the atom that has mass. So protons have mass, and it has a mass value of 1. So it's important that you know that protons have mass. You've then got your electrons, which we said were floating around on shells, and they are opposite charges to that of the protons. So they are negatively charged. Okay, so they're -1. They have a slight mass, but essentially it's called negligible mass, but we're just going to say 0. So they don't have mass, and a good way of remembering it is whatever's in the nucleus of the atom has mass. If it's not in the nucleus of the atom, then it doesn't have mass. And then the final part are our neutrons. And just like I said for the protons are positive. They both begin with P. Neutrons are neutral. Okay, so they do not have a charge, but they're in the nucleus of the atom, so they must have mass. And you do need to be able to remember that protons are positive and have a mass of 1. Electrons are negative, have negligible, so we'll say 0 mass. Neutrons are neutral and have a mass value of 1. So you are expected to do that. In addition to that, the periodic table actually tells us lots of information. I'm just going to zoom in slightly on this. It tells us lots of information about the atom. So for example, the periodic table has got key information within it. And I'm just going to get my other copy of the periodic table here so you can see what I'm talking about. You'll see on the periodic table there's a little key, and we do go into a bit of detail on this in the periodic table video. And that key shows the proton number is at the bottom of the element in the periodic table, and the mass of the atom is at the top. So it's important that we use this key because you are sometimes expected to be able to identify the number of protons, neutrons, and electrons that elements have. And you also need to use this to be able to draw atoms. So it's important we're able to interpret that. And that's what we're going to look at now. So first thing I want you to be aware of is that we know that the elements are arranged in groups, but that also tells us a little bit about the shells that they have when it comes to drawing the electron configuration. So the first period, which is the name we give to the row, it has one shell. The second period or row has two shells, and it keeps going down like so. And you only need to know up to calcium, okay? So that's the element you need to be able to draw up to. But as you can see, as you go down the group, the size of the atom in itself is getting bigger, so we have got more shells. If I pick an element such as, say, fluorine, so here's fluorine here, I can see fluorine has got two numbers attached to it. It's got 19, which we know from the key is the mass of the atom, and it's got the number 9, which is the proton number. So I'm going to write that out because it's important we're able to interpret what that information actually tells us. Okay, so there's fluorine and the two numbers. Now we've talked about protons, electrons, and neutrons. And if you remember, we said that actually these two numbers can tell us the number of protons, electrons, and neutrons that atoms have. The first thing I will say is the top number is never an answer. And this is something that we notice quite a lot when we're marking chemistry papers. If, for example, you're asked to identify the number of neutrons, students seem to pick this number, okay? This number here is never an answer to a number for protons, electrons, and neutrons, okay? So just, I'm going to underline that. I might even get a green pen because I like my green colour, okay? So that is never an answer. What you do need to know, though, is that from the periodic table, I know from the key that the bottom number is the proton number. So I know in the case of fluorine, that fluorine has got 9 protons. Okay, so I can see quite clearly, dead easy, proton number is 9. Now, what you do need to know is that in an atom, okay, so we're not talking about ions here, in an atom, the number of negative charges to positive charges are equal. Okay, so atoms have no overall charge. And that's because the number of protons, which are positive, so in this case 9, equals the number of electrons, which are negative. So the proton number is also telling me my electron number. So in this case, I have got 9 electrons. So the proton and electron number are always the same when it comes to identifying the number when we're looking specifically at an atom. The top number we know from the periodic table, that is called atomic mass. And we just said that the mass of the atom is the nucleus of the atom. So that is our neutrons added to our protons. So if I'm being asked to work out the neutron number, I essentially need to first of all look at my proton number. And here I can see I've got 9 protons. So then I'm working out the difference between these two numbers in order to work out my neutron number. So the difference between 19 and 9 is obviously 10, and that is the number of neutrons that it has. So it's important you're able to practice that. So what I'm going to get you guys to do now is on the next page in your booklet, you have got some examples, and you will need a periodic table to help you to do that. So just take a minute, pause the video. Work your way through and then come back and check that you were able to get something similar to what I've got here. Okay, so hopefully you were able to do that. We're going to do this now very quickly. So it's asked first of all to work out calcium's number of protons, neutrons and electrons. So calcium is here. The two numbers I have are 20 and 40, and don't forget, can I ever have 40 as an answer? The answer is no. So we don't choose 40. What we do instead is work out the proton number. So in this case, the proton number is 20. And then we know that the positives and negatives are equal. So if I've got 20 positives, that means I've also got 20 negatives, so 20 electrons. To work out the neutron number, I work out the difference between these two numbers here, and that, of course, is 20. Okay? Nitrogen is 7 and 14, so I know it's got 7 protons, 7 electrons, and the difference between 7 and 14 is 7, so that's what we should have got for that. Neon is 20 and 10, so 10 protons, 10 electrons, and the difference is, in this case, between 20 and 10 is 10. Hydrogen's a bit of a tricky one. So here's hydrogen. So I can see that hydrogen has got 1 proton, which means it has also got 1 electron. And the difference between 1 and 1 is 0. So it doesn't actually have any neutrons. So that sometimes comes up, so it's a little bit trickier. And then finally, oxygen is 8 and 16. So you should have 8 for your protons, 8 for your electrons, because your positives and negatives are always the same in an atom. And then we're working out the difference between 16 and 8, which in this case is 8. So you are expected to be able to do that. It does come up quite a lot, so it is important you are able to interpret the periodic table and actually work out the number of protons, neutrons and electrons. And this links in nicely to the next part, which is our electronic structure. Can't quite see it because of the way it's folded over. But you are expected to use those numbers, okay, to then draw the electronic structure of an atom. And I'm going to give you some ways to do this. We'll practice a couple together. I'll then set you off to do some on your own. But essentially there are rules, and it's important we know the rules. Okay, and the rules are quite straightforward, okay? As you can see from my diagram, these dotted lines here are what we call shells. Okay, so these are our shells, and on those shells sit our electrons. So if I number these shells 1, 2, 3, and there is a 4th shell that you have to be aware of, we then have rules about the number of electrons each shell can hold. So shell number 1 can hold a maximum, okay, of 2 electrons. Shell 2 can hold a maximum of 8 electrons. Shell 3 can hold a maximum of 8 electrons. And as we only need to know up to calcium, okay, shell 4 will hold a maximum, well, we'll say in this case 2, but you can have it up to 8. Okay, so just be aware, this is the maximum number that can go in each shell. So we already know how to work out the number of electrons because our electron number is the same as the proton number because positives and negatives balance out. So I'm going to pick beryllium. So beryllium here has got a mass of 9 and a proton number of 4. So if there's 4 protons, that means there's also 4 electrons. So if I draw beryllium, okay, so beryllium, I'll do the symbol for you just so you can see the numbers. Okay, so there is beryllium there. I know from the rules the first shell can hold 2. So I do 2 electrons in my first shell, and then I do 2 electrons in my second shell. And we would then write the electron configuration for this atom. And all that is telling you the number of electrons in each shell. So I can see in my first shell there are 2 electrons. I do a comma. And then we've got 2 electrons in the second shell. So that would be the electron configuration for beryllium. Now, what this also tells us is what group the element is in. okay? And that's because the number of electrons on the outer shell tells you the group. So beryllium has got 2 electrons in their outer shell, and lo and behold, beryllium is in group 2. So we'll do one more. We'll do oxygen. So oxygen's 2 numbers are 16 and 8. Okay, 16 and 8. There's oxygen. Remember, our bottom number is telling us our electron number because the protons and electrons are the same. So there's 2, 3, 4, 5, 6, 7, 8. So again, that's how we'd fill that in. I can tell its electron configuration would be 2 in the first shell and then 6 in the second shell. What group is it in? Well, it's got 6 electrons in its outer shell, so it must be in group 6. And indeed, it is. So I'm going to give you an opportunity now to practice some of those. So on the next page, you've got a blank page. I'm going to write out some elements. You're going to draw the electronic structure. So we'll go straight forward. So there's sodium, which has got 23 and 11. We've got fluorine, which is 19 and 9. And we'll pick a noble gas, shall we, which is neon, which is 20 and 10. So take a minute, pause the video, okay, give that a go, draw the electronic structure, don't forget to include the electron configuration, but pause the video, give that a go, and then come back and see if you're able to do it just like I'm going to do now. Okay, so bottom numbers are the one we're looking at. It's got 11 protons, so therefore 11 electrons. I've followed the rules that 2 can go in the first shell, then 3, 4, 5, 6, 7, 8, 9, 10. So again, the maximum it can hold in the second shell is 8. That means I need a third shell. In this case, there is 1 electron in that outer shell. And I know that that is in group 1. Its electron configuration would be 2, 8, 1. Fluorine, tick it off then guys. Fluorine has got 9 protons, so therefore 9 electrons. We follow the rules, 1, 2, 3, 4, 5, 6, 7, 8, 9. I can see it's got 7 electrons in its outer shell, so is part of group 7. Its electron configuration would be 2, 7. And then finally, neon has got 10 protons, so therefore 10 electrons. So 2, 3, 4, 5, 6, 7, 8, 9, 10. Its configuration would be 2, 8. And I know that it's got a full outer shell. So that tells me it must be in group 0. Okay, or group 8, as it used to be called, group 8 back in the day. So group 0, because all of those elements have got a full outer shell. Okay, so that's what it means when it comes to drawing the atoms. What you also need to know about is something called isotopes. Okay, so isotopes are essentially, well, I always like to teach isotopes like when you go shopping with your parents and you're looking at the different versions of Coca-Cola. You get Pepsi Max, you get Coke Zero, Diet Coke, Diet Pepsi, whatever it is. They're all examples of Coca-Cola, but they're just different versions of them. And that is what isotopes are, okay? So they are essentially the same element. So you can see I've got oxygen, okay? But they vary slightly. And they vary because if you look at the number at the top, they vary because actually they have got a different number of neutrons. So looking at the mass numbers here, you can see that the mass number is changing, but my proton number is staying the same. And the difference between these two numbers we know are our neutron number. So isotopes essentially are atoms of the same element. Okay, just like the Coca-Cola in the shopping market. Atoms of the same element with a different number of neutrons. And You are expected to be able to notice that. I've seen questions asking you to define it. So know it's about the fact that they're the same element, but they've just got different numbers of neutrons, and that gives them slightly different properties. So we're going to link this now into a calculation where we are often asked to calculate the relative atomic mass of specific types of isotopes. And that ties into a calculation that you do, I'm afraid, need to know. And this is the calculation here. So RAM, which is the relative atomic mass. So that's the number at the top. So relative atomic mass is equal, and I'm going to start using some fancy sciencey words here, I'm afraid, the sum of, in brackets, isotope abundance multiplied by the mass. Okay, so if I've got 3 isotopes, I want to know the abundance for each one. I want to know the mass for each one as well. So what I need to do is make sure I know to calculate the relative atomic mass of isotopes together. We do this by a calculation where we take the sum of the isotope abundance. Now that's a fancy word. So abundance just means essentially the amount we have of it. So that usually is a percentage, okay? And we then divide that by the sum of the abundance. Now, this might sound a bit strange, but I'm going to show you it in terms of an actual exam type question. So here is a typical isotope abundance question. And as you know, we always talk about bugging the exam question, but this is usually worth 2 marks, sometimes 3 if there's more than 2. But essentially it's saying the table below shows the mass numbers, okay, and we know that from the equation, right, is the sum of the abundance times the mass, okay? So just remember, that's what we're looking for, and we're then dividing it by the sum of the abundance. Okay, so I'm going to work this out for you now. So the table below shows the mass numbers. So you can see mass is part of my calculation, and here are the mass numbers of these 2 isotopes and the percentage abundance of the isotopes of gallium. And we know that the sum, okay, so sum means together, so we're adding these together. Essentially, we're taking the abundance of the element, the mass of the element, timesing those 2 numbers together. And because there's 2 of them, we do that twice, and then we divide it by the sum of the abundance. So the question's asking me to calculate the RAM, relative atomic mass, and it's important that I give my answer to 1 decimal place. Okay, so I plug my numbers into the calculation. So the RAM, the relative atomic mass, is the abundance of the element times by the mass. So this element here has a mass of 69 and an abundance of 60. Okay, but as it quite clearly says in the calculation, it's the sum. So I've then got to take my second element, okay, and I'm going to do the same. So I'm going to have the mass, which is 71, and I'm timesing it by the abundance. Now to get the sum of that, I'm going to add those 2 numbers together. So I've got my calculator here. So you can see I've got my 2 numbers. So we've got 69 times by 60 gives me 4,140. And I'm adding that to 71 times by 40, which is 2,840. So I add those 2 numbers together, and that gives me a total of 6980. And we know that we then divide it by the sum of the abundance. So in this case, it's those 2 numbers added together, which would be 100. And that gives me a relative atomic mass of 69.8. and that is to 1 decimal place. Okay, so that's what we're talking about when we're actually talking about calculating the relative atomic mass. You take the isotope abundance, you multiply it by the mass. If you have more than 2, you have to then add them all together. So you do that calculation, then add it to the next one with that calculation, the next one, and then we divide it by the sum of the abundance. Okay, here's the final one. What I might get you guys to do is give this question a go. We've got 3 isotopes here. Again, I'm being asked to calculate the RAM. So we know that that is percentage abundance times by the mass, added to of isotope 1, the percentage times the mass of isotope 2, added to the percentage times the mass of isotope 3. So why not pause the video, give it a go, and then we'll see if you can actually do this one. Okay? So hopefully you're able to do that. So let's have a little look if you get what I get. Again, remember, we're asked to calculate the RAM. And this time it's asking me to give my answer to 3 significant figures. And it's always important you don't forget that, because that is usually a mark. So here we go. Isotope 1, we have got 24. That is its mass. And I'm timesing it by 78.6. Okay? And that gives me 1886.4. And then I'm adding it to isotope 2. So 25 is the mass, times by 10.1, which is the percentage, and that's 252.5. And then I'm adding it to isotope 3, 26 times by 11.3, which is 293.8. And it's important you show your working, because if you don't show your working, then actually you will lose marks. And I'm then dividing that by the sum of the abundance. So we've got 78.6 plus 10.1 plus 11.3, and that equals 100. Okay, so let's do the calculation then. So 1886.4 plus 252.5 plus 293.8 equals that. I'm dividing it by 100, and we then get an answer. Now the question asks me to do it to 3 significant figures. Okay, so that would give me an answer of 24.3. Okay, and that's the answer I'd be looking for there. Okay. All right, so that's the second part of the fundamentals of chemistry. I hope you found that useful, and check out my other videos when you get the chance. All right, thanks everyone. Bye.